Hey there, organickers. Let's see if we can get a little practice at recognizing tetrahedral stereocenters. When you're looking for tetrahedral stereocenters, obviously the first thing you want to look for are tetrahedral carbons. Next, if you're looking at a skeletal structure, you want to ignore any carbons that are only showing one or two bonds. If a carbon is showing two bonds, that means that the other two have to be hydrogen. If the carbon is only showing one bond, the other three must also be hydrogen. So ignore all of those carbons. You're really looking for tetrahedral carbons that are showing 3 or 4 bonds. If they're showing 3 bonds, that means that the fourth atom bound to that carbon must be a hydrogen. If we look at this molecule here, you can see that we have 2 tetrahedral carbons that are showing 3 bonds. But this one right here has 2 identical groups attached to it. It has 2 methyl groups, so that can't be a stereocenter. This carbon, on the other hand, has 3 unique groups attached to it, so this carbon is a tetrahedral stereocenter. The representation that I'm showing you is not indicating any stereochemistry or any configuration of the stereocenter. This could be one isomer or the other isomer, or it could be a mixture of isomers, and you would have no way of knowing this. However, if I draw wedges or hashed bonds, that indicates to you the configuration of the stereocenter. These are the 2 stereoisomers that I can draw. One has the hydroxyl group coming forward. That means that the hydrogen that's attached must be going back. The other isomer has the hydroxyl group going backwards, which means that the hydrogen that's attached must be coming forward. Let's see if we can determine absolute configuration of our stereocenters. The first thing we want to do is assign priorities. My oxygen is going to be number 1. Now I have to compare the 2 alkyl groups. Isobutyl is going to have a higher priority than the methyl group. So isobutyl is 2, methyl is 3. I'm looking at this stereocenter in the proper orientation, or in other words, the hydrogen that's attached to the tetrahedral carbon, which would be the lowest priority group, is oriented away from me. When I trace my path from high to low, that path goes in the counterclockwise direction, so this is the S isomer. That must mean that the other isomer that I've drawn is the R isomer. I want to take just a minute and point something out to you with respect to the R isomer. If I label the priorities of my groups and I trace my path from high to low, my pathway is going in the counterclockwise direction. But notice that I'm looking at this stereocenter from the wrong orientation. This stereocenter has the hydrogen, or the lowest priority group, oriented towards me. So this is another way that you can determine absolute configuration of a stereocenter without necessarily having to construct a model, although models are the best way to visualize these three-dimensional structures, or without needing to reorient the molecule on paper, because sometimes you can get tripped up when you do that. If you're looking from the wrong direction and your priorities of your groups from high to low are going counterclockwise, instead of calling that isomer S, you would call it R. Let's have a look at this molecule. How many stereocenters do I have? I have 2 tetrahedral carbons that are showing 3 bonds, but this one, again, has 2 identical groups attached to it, so that carbon is not a stereocenter. On the other hand, this carbon here has 3 unique groups attached to it, so yes, this would be a stereocenter. I can draw 2 stereoisomers, one that has the NH2 group coming forwards towards me, and the other one that has the NH2 group going away from me. Let's see if we can determine absolute configuration. First, we want to label the priorities of our groups. Nitrogen would be number 1, followed by the carbon that has the oxygen attached, followed by the isopropyl group. My path from high to low is going in the clockwise direction, so this isomer would have the R configuration. This must mean that my other isomer has the S configuration. My path from high to low is going in the clockwise direction in this isomer, but note that I'm looking at the stereocenter from the wrong direction. the lowest priority group, the hydrogen, is coming towards me. How about this molecule here? Well, I have two tetrahedral carbons that are each showing 3 bonds. This one has 3 different groups, so that's a stereocenter. This one also has 3 different groups, so that's a stereocenter as well. You'll often see that we draw a little asterisk next to the carbon to indicate that that is a stereocenter. So what does this mean in terms of the stereoisomers that I can draw? Each one of those stereocenters can exist in 2 possible configurations. What this means is that I can have 4 different combinations of those orientations. I can have both of them coming forward. I can have the methyl group forward, the NH2 backwards. I can have both groups going backwards, or I can have the methyl group backwards and the NH2 coming forwards. So when you see multiple stereocenters, we can determine the maximum number of possible stereoisomers. This is going to be 2 to the nth power, where n is the number of stereocenters. In this case, I have 2 stereocenters, so 2 squared is equal to 4. You'll find some situations where you'll see molecules that don't have the maximum possible number of stereoisomers. This is a special case, and we're going to talk about these kinds of molecules a little later in this video. Take a minute and see if you can determine the absolute configuration of these stereocenters. You really have to just assign configurations for the first molecule. You're looking at both stereocenters in the proper orientation, so that should be pretty straightforward. Once you assign those 2, you should be able to label the rest of them pretty quickly. Go ahead and pause the video and make all of those assignments. Well, let's see how you did. Here are our absolute configurations, and you'll note that there are 4 different and unique combinations for these stereocenters. This is a pair of enantiomers. If we have the SS isomer, that must mean that its mirror image is the RR isomer. This is also a pair of enantiomers. On the top, we have the 2R, 3S isomer, and on the bottom, we have the 2S, 3R isomer. So the mirror image of 2R, 3S must be 2S, 3R. What's the relationship between these 2? These are stereoisomers that are not mirror images, and we call those diastereomers. Stereoisomers that are not mirror images. These are also stereoisomers, which are not mirror images. This is a set of diastereomers as well. These 2 are diastereomers to each other, and these 2 are diastereomers to each other. Let's look at a few examples of cyclic molecules. Here we have methyl cyclohexane. I only have 1 carbon that's showing 3 bonds. Would that carbon be a stereocenter? Let's draw the methyl group, or the substituent, in the 2 possible orientations. Let's try to decide if they're superimposable or not. I want to point out to you that if my methyl group is going back, that must mean that my hydrogen is going forward. If I draw an axis through this molecule, and then I rotate around that axis, that's going to bring the methyl group forward and the hydrogen back. Now let's see if we can superimpose these 2 molecules. They superimpose exactly. So this molecule is achiral, and it is achiral by virtue of having a plane of symmetry. There's a plane of symmetry that lies right along this axis that I've drawn here. Or in other words, it's going to bisect carbon 1 and carbon 4 of my cyclohexane ring. It's also going to bisect the hydrogen and the methyl group as well. Everything on one side of the plane of symmetry is the mirror image of the opposite side. Let's look at another example. Very similar. Now we have a disubstituted cyclohexane ring. If I draw an axis through this molecule, through carbons 1 and carbon 4 of the cyclohexane ring, and I rotate around that axis, I think you can see that I'm going to regenerate this structure here, and those 2 would be identical. So this molecule is also achiral by virtue of having a plane of symmetry. I want to point out to you another way of thinking about this. I can see that I have a methyl and a hydrogen, but I need to decide if the other groups are the same or different. One way that I could do this would be to work my way around the ring 1 atom at a time until I come to the first point of difference, or until I come to the same place from both directions. Let's look at another example of a substituted cyclohexane. This time we have a tri-substituted cyclohexane, and I have one carbon that's showing 3 bonds and one carbon that's showing 4. But this carbon that's showing 4 bonds has 2 methyl groups, so it has 2 groups that are identical, so that can't be a stereocenter. How about this carbon? Well, I have a methyl and a hydrogen, and I can draw those in the 2 possible orientations. Now I need to figure out if these 2 are superimposable. One thing that I could do is draw an axis through this molecule and rotate around the axis, and hopefully you can see that that will give me this new representation here. And if you can't see that, I would strongly recommend that you make a model and do this with a model. Now let's try to superimpose this new representation that I have with the original. While my methyl groups line up here, and they're both pointing in the right direction, these substituents here are not lining up. So this molecule is chiral. Again, another way that you could think about this is you want to work your way out the ring to the first point of difference. There's my first point of difference. The 2 substituents attached to this carbon that make up the ring are different. I want to show you another example, and this time we have a disubstituted cyclopentane. Immediately you can see that I have 2 carbons showing 3 bonds. Could these 2 carbons be stereocenters? Let's draw our possible orientations. I can have the cis isomer, and let's draw the mirror image of that, and I can have the trans isomer, and there's its mirror image as well. Let's assign the configurations. Go ahead and pause for a minute and see if you can do that. Well, here's our absolute configurations. I want to point out to you that if I rotate this molecule 180 degrees in the plane of the screen, that's going to make it superimposable on this one. That means that this pair on the top are identical. They're not enantiomers to each other. And another way that I could think about this is say I have a plane of symmetry in this molecule. So the cis isomer is achiral by virtue of having a plane of symmetry. For the trans isomer, you can see I have the RR and the SS. These 2 indeed are mirror images. And there's no way that I can superimpose one of these on the other. If you can't see that, make a model and prove it to yourself. The trans isomer, therefore, is chiral and has no plane of symmetry. So the molecule that has stereocenters but is achiral has a special name. We call that a meso compound. A meso compound is a molecule that has tetrahedral stereocenters, and yet it is achiral. See if you can't identify the tetrahedral stereocenters in this molecule, cholesterol. Again, remember that you're looking for tetrahedral carbons that are showing 3 or 4 bonds and that have 4 unique groups attached. Go ahead and pause and see what you get. So here are all your tetrahedral stereocenters. There are 8 of them. So there are 2 to the 8th possible stereoisomers for cholesterol. There was an awful lot of information to take in on this video, and we'll be talking a lot more about this during class. However, you may need to watch this video again